In this video, we're going to talk about optimization and do some examples in SageMathCloud. Optimization is where we want to maximize or minimize some quantity given some constraints. For example, maybe you want to make a cylindrical can that holds 1 liter, that's the constraint, and you want to minimize the surface area. Our goal is to maximize or minimize some function. We know that that will occur either at a local max, or min as the case may be, or one of the endpoints of the domain. So we want to find the critical points of our function, that is where the derivative is 0 or undefined. And then if we just put all those critical points into the function and see which one is the biggest and which one is the smallest, then that would be the maximum or minimum value that we want. The challenge of these optimization problems is usually to convert the statement of the problem, which is a paragraph in English words, into mathematical equations. And then we need to somehow work with those equations to get out a function of a single variable that we can maximize or minimize using the derivative. These are the steps that I will follow in general. First, define the variables that are involved. Second, if appropriate, draw a picture. Third, determine equations that relate all those variables. 4, use the constraints given in the problem to eliminate as many of those variables as you can. Our goal here is to write whatever quantity we want to maximize or minimize as a function of a single variable. Once we've done that, step 5, take the derivative. Step 6, set the derivative equal to 0 and solve for the variable. Find where the derivative is undefined, if there are any. Those are all the critical points. Step 7, plug in the critical points and the endpoints of the domain, if there are any, into the function. Now if the endpoints of the domain are not included in the domain, you might have to take limits there instead. Then the largest or smallest value that you get out of all of those things is the absolute max or absolute min, depending on what you're looking for. I'm going to go ahead and use Sage to graph so we can just check our answer. And finally, step 9, don't forget to answer the original question. Sometimes the question will ask you for the maximum value or the minimum value. Sometimes it will say what values of the variable or variables give you that max or min. Sometimes it asks you for all of that. So make sure that you answer the question and use correct units in these applied problems. Here's the first example. So we have a rectangle. The perimeter is given. I want to maximize the area. So my variables involved are the dimensions of the rectangle. I'm going to call them x and y, and the area I'll call A, the perimeter I'll call P. So here's a picture. I got a rectangle with dimensions x and y. Step 3, set up equations. I know the area of a rectangle is x times y. I know the perimeter of a rectangle is 2x plus 2y. Those are my equations. I now want to eliminate variables. I'm trying to maximize the area, so I want to rewrite this area equation with a single variable. To do that, I'm going to have to use the perimeter equation. I'm told that the perimeter is 100. So if you replace p with 100 in this perimeter equation, solve for one of the variables. I'm going to solve for y. I'll let Sage do it. So Sage tells me y is negative x plus 50. I'm then going to substitute that for y into the area equation. So the area is x times y, and I'm going to replace y with negative x plus 50, which is what y equals. And I'll get this area equation as a function of x alone. Once you have the quantity you want to maximize, in this case area, once you have written that as a function of a single variable, you're ready to take the derivative, find out where the derivative is 0. So here I define my area function. I took the derivative of A. I asked Sage, where is the derivative equal to 0? I solved that equation for x. Sage tells me there is one place. Oops, I forgot to hide that little text there. One place, x equals 25. Is the derivative ever undefined? Well, no. The derivative, here's the derivative. It's this line. Only issue we have to worry about with that line is the endpoints of the domain. So x and y are distances, so x and y have to be positive. Now that puts a limitation on what y can be. Remember, here y is, the fact that y has to be positive puts a limitation on x, because y is negative x plus 50. If x gets too big, that would make y negative. If x is bigger than 50, y would go into the negative land. So x has to be between 0 and 50. Alright, so we're going to take our one critical point where the derivative is 0, x equals 25. We're going to take the endpoints of our domain, 0 and 50, and we're going to plug them into the area function. And we'll see which one gives us the biggest. And the biggest area here is 625. That came from x equals 25. So that is the answer that we want. I'm going to go ahead and check my work with a graph. I'm going to graph the area function. And I can see, okay, it looks like somewhere here around x equals 25 is where this area reaches a peak. Now, this graph does not check whether or not you set up the area function correctly. This is only checking to see if you found the max correctly. So make sure this area function is right to begin with. Finally, what's the answer? The question says, well, what did the question say? Let's go back to the question. Find the dimensions that maximize the area. Okay, so the question was not what is the maximum area, but find the dimensions. One dimension is 25. That's x. The other dimension is y. I have an equation for y. Y is negative x plus 50. So if I put x equals 25 into that equation, it turns out that y equals 25 as well. So I see that the rectangle with a maximum area and this given perimeter is a square, 25 meters by 25 meters. And that's the end of example 1. Alright, here's example 2. I have another rectangle, a little more complicated this time because the edges of this rectangle are weighted. I'm going to build a wall around this rectangular garden. I'm going to have a brick wall on one side that's $30 per foot, and the other three sides is going to have a metal fence, $10 per foot. I have a given area I want, 1,000 square feet is the desired area of this garden. What are the dimensions that will minimize the cost of this material for the metal fence and the brick wall? So I have several different variables. A, the area of the garden. C, the cost for the wall and the fence. And then the dimensions I'll call x, y. I'm going to just choose to put the brick along one of the y sides. So here's my picture. I have a rectangle. Three sides are $10 per foot. One side is $30 per foot. All right. Set up my equations. So area is x times y. Cost is the cost per foot multiplied by the number of feet. The number of feet here of this side, for example, is y. Y feet multiplied by $30 per foot gives you the number of dollars. So 30y is the cost of this one side. 10y is the cost of this side over here. $10 per foot for the fence multiplied by y, this width here. 10x is the cost of this side. 10x is also the cost of this side. So we have a 30y, 10y, 10x, 10x, which gives us 40 y's and 20 x's. Those are our equations. I want to minimize the cost. So I want to rewrite this cost formula using only a single variable. To do that, I will use the area equation. I was told that the area is 1,000. Plug that into the area equation. Solve that for one of the variables. I'm going to solve for y. So you just divide both sides by x here. You get y is 1,000 over x. I'm then going to substitute that value of y into the cost equation. And I get cost as a function of x alone. So 40 times y is 40 times 1,000 over x plus 20x. And there I simplified a little bit. Once you have the quantity to be minimized, cost, written as a function of a single variable, x in this case, you're ready to take the derivative. So to find the function, take the derivative, set it equal to 0, solve for x, and I get two answers right here. Now remember, x is a dimension, so it can't be negative, so I can ignore the negative solution, so I just get this one, 20 times the square root of 5, which is roughly 44.72. Now what's the domain of this cost function? Same as the domain of this guy, so x has to be positive. There's no limit on how long x x can get. So theoretically anyway, x could go off to infinity as long as y could be small enough. Now physically you're not going to be able to build a brick wall if your y side is like 0.000001 feet or something, but let's just kind of not worry about that. So I have 3 points to worry about. I have my one place where the derivative is 0, the 44.72, and then I have a 0, and then I have infinity. So I put the critical point into the cost function, and I got this answer, so roughly $1,800. What happens at 0 or infinity? Now 0 or infinity are not in the domain. Those are just the endpoints of the domain. I can't plug those into the cost function. I can take limits though. So that's what I'm going to do in this case. I'm going to take the limit of the cost function as x approaches 0 from above. And the answer is infinity. I'm going to take the limit of the cost function as x approaches infinity. And the answer is infinity. So in both cases, as either the x gets really small, when x gets really small, that means y has to get really big, so the cost explodes. And if x gets really big, y is small, but x is still huge, so the cost explodes. That means the minimum cost has to be this guy from our critical point. All right, let's check the graph. Sure enough, it looks like somewhere here around between 40 and 50 is where the minimum is. So that's green with what we found before, and you can see that the cost just explodes as you go off in either direction towards the endpoints of the domain. So the question says, what dimensions minimize the cost? So x should be this 20 squared of 5, or approximately 44.72. Y, I remember I have a formula for y, so I just take this x and I put it into this formula for y and calculate, and this turns out to be 22.36. And remember, the brick wall goes along one of these y sides, so this should make sense. The brick is more expensive, so I would expect the brick side to be shorter, and it is. It's like half the length of the other side. Okay, example 3. I'm going to construct a box with no top using a 5 foot by 4 foot piece of cardboard. I'm just going to cut out squares from each of the corners and fold up the side, and I want to maximize the volume of the box that results. So here is the picture I have. I got 5 feet here by 4 feet there. I'm going to cut out a corner. I'm going to fold up this side here. So this part sticking out, I'm going to fold right along this and then this side I'm going to fold up right along here. I'm going to fold up this side, and right along here I'll fold up that side, and right along here I'll fold up that side, and I'll make a little box. The height of this box will be the length of this side that I've cut out. So this dotted line is where I'm going to cut this h by h square. That will result in the height of the box. Let's go down here. Volume, sorry, I skipped over step 1. Volume, length, width, height, and I'm going to cut out by h square. So the h is going to be the height, like I said. Alright, so I know volume is length times width times height. What is the length? Well, the length here is not 5 feet. Remember, 5 feet is this total, but I'm cutting off an h from this side, I'm cutting off an h from this side, so the length is 5 minus 2h. Similarly with the width, I got 4 feet total on this side, but I'm going to cut off h here, I'm going to cut off h here, and that'll leave this segment 4 minus 2h left over for the width. So I'm going to plug those two equations into this volume equation, replace L with 5 minus 2h, replace W with 4 minus 2h, and now I have volume written as a function of h alone. And there's the simplified version. If you want Sage to do that multiplication for you, there's an expand command which will multiply that all out, and you'll get that cubic function. Alright, I'm going to define v to be that function. It's a function of h. I'm going to take the derivative as with respect to h of this function. I'm going to find out where this derivative is equal to 0. And Sage gives me two answers. Now, don't just knee-jerk say, oh, this one's negative. No, it's actually not negative. This part's negative, but we're adding 3 halves. So if you convert these to decimals, you get these two answers, roughly 0.74 and 2.26. Which one of those is going to maximize our volume? Well, I'm going to plug those two things in. So I copied and pasted from the answer up above. I plugged it into the original V, the volume, converted to decimal, and I got 6.56 from the first one. That's the 0.74, gives me a volume of about 6.5. If I plug the second one in, I get this negative volume. So that's obviously not the maximum. It's a little disturbing. I have negative volume. In a minute we'll see why that turned out to be negative. So it looks like the first value is the one we want. The 0.74 gives us the maximum volume of about 6.56. Unless it happens at the endpoints, which is not going to be the case. Now, what are the endpoints of the domain here? And we know h needs to be positive since it's a length. We also have some limits on how much we can cut off. If you look at this picture, this thing is only 4 feet wide here, so I can't cut off more than 2 feet from each side. If you cut off 2 feet here and you cut off 2 feet there, there's nothing left for the width, so you don't end up with a box. So h needs to be smaller than 2 so that there's something left on this side. Alright, h smaller than 2. If you plug in h equals 0 or h equals 2 into the volume formula, you get no volume. So h is 0, of course, that you don't cut off anything, there's no box, there's just flat thing, so there's no volume. If h is 2, you've limited the width, so you just fold a piece of cardboard in half and you have no box. So no volume at the end. That tells us the maximum volume is the 6.56, which occurs here in the neighborhood of 0.74. If we check the graph, we see that roughly 3/4 somewhere around in here is where we get the maximum. That confirms this 0.74 we got from our calculations. So step 9, answer the question. The question is, how much should we cut off from each corner? So roughly 0.74 feet from each corner. It gives us what we want. And those are some optimization examples.